We are going to now move on to our second talk of the day today in this first session, which will be given by Sayan Mitra.
Can you see my screen now?
Yes, we can. And let me give a brief introduction. Sayan Mitra is a professor of electrical and computer engineering at the University of Illinois at Urbana-Champaign, where he moved after, well, he did his PhD at MIT, and then had postdoctoral positions, and then visiting positions also at Caltech, Oxford, and TU Vienna. So Sayan's research is in algorithmic analysis of autonomous systems, such as self-driving cars and spacecraft. And he has developed, his lab not only develops the algorithms and tools, but they also commercialize these algorithms and tools. So it'll be interesting to hear his perspective from both the the academic development side, as well as what it takes to have the tools commercialized and used in industry. Thank you, Sayan, for giving a talk, and we look forward to your talk.
Thank you very much for the kind introduction, Claire. Can you hear me all right? Okay, great.
Yes, we can hear you.
So good morning, everyone, and it's a real privilege for me to be speaking to you today. So, as Claire introduced, my research is in this area of design automation for autonomous system. The focus for design automation research is on building algorithms and tools that can accelerate the development of systems. And you're probably familiar with the electronic design automation industry, and this is a mature area of research now. But this is the area that provides the hardware description languages, the simulators, the test generation tools that have really accelerated the exponential growth of the semiconductor industry. Now, something like that is currently not mature for robotics and autonomy, but it's a very exciting time to be working in this area. For example, imagine a tool that can generate executable code from a high-level program for different robot hardwares or different platforms, automatically adjusting for the variations in the hardware. Or imagine a verification and validation tool that can quickly zoom in and find the difficult corner cases and allows the engineers to go smoothly between models and data. So these types of technologies currently do not exist, but a community is coming together across machine learning, control theory, verification in building these types of technologies. So today I'm going to talk about two works. The first one is about a new programming language for distributed robotics. And the second part is going to be about verification. So let's dive in. So consider building a delivery application. You have a fleet of robots and a sequence of tasks. And the goal is to develop an application where each target is visited once, and the robots should not collide. So pretty straightforward. And by replacing the visit action with other actions like take a picture, deploy some chemical, you can easily see that this is an archetype for many other applications for warehouse management, package delivery, mapping, surveillance, agriculture. So how would you develop an application like this? Okay, so you can use different techniques, but let's say you are just coding up this application. So at a high level, the flow chart for writing this application is pretty straightforward. You have a robot and it has to first assign itself to one of these targets, and then it has to go to this target to accomplish this task. Now, if you look inside this assignment part, well, if you have some sort of a shared memory or some shared information like a table which maintains all the assigned tasks and the paths that the robots are taking to do these tasks, then again, it's a pretty straightforward thing. So each robot could just iterate through the different tasks. And if you have this shared infrastructure, might as well use that for congestion control. You can avoid going to the same part of the workspace and go to some place where there is not as much congestion. And then once you've assigned a task, then there are these other problems to be solved. Like you have to plan a path, avoiding the obstacles, And then you have to follow the path, and that involves some low-level control of the platform. Okay, so at a high level then, if you look at this application, then there are some building blocks. And if you have these building blocks, then writing this code is not too difficult. And so we have identified 3 building blocks here. There is the path planner, there is a waypoint following or the controller for the paths, and there is this shared data structure that has to be maintained. Now, so the answer to this question of how much effort does it take to build an application like this is, it's a reasonable amount of effort if you have good implementations of these building blocks. But it turns out that each of these building blocks or abstractions are actually hard problems. So for example, path planning is a well-known hard problem. Even now, you have hundreds of papers being submitted to robotics conferences to solve that problem. Distributed shared memory is a hard problem. So this is a problem that has been studied for more than 3 decades. In general, it is not solvable if you have message delays and failures. Under some restricted conditions, you can solve it. So from the point of view of an autonomy engineer or a roboticist, each of these things can seem like a rabbit hole, and debugging and putting them together can be a lot of work. So this need not have to be the way of going forward to build safe autonomy. There are many other engineering domains where there are powerful abstractions that have been very helpful. So my favorite example is the x86. This is the assembly language that defines how the hardware talks to the software. And the important thing is it defines what operations can be performed, like add, and, not, what have you, and what data movement is allowed between memory and the CPU. And it doesn't specify how these operations are to be performed and how data movement has to happen. And this is quite nice because this leads to separation of concerns. Hardware companies can implement, make the design choices to build their microarchitecture implementing these operations. And on the other hand, software companies can have their compilers, programming languages, and applications that can compile down these high-level programs to the assembly language, which is then executed on the hardware. And these types of abstractions have other benefits also. It's portable, it's quite expressive, and it's stable. So the developers can count on the same contract between the hardware and the software. So unfortunately, in autonomy and robotics, the situation is not like this right now. In fact, it's more like this situation where every device needs to have its own power supply. Maybe it's not quite as bad, but it's more like this than like in the x86 world. So addressing this in the context of distributed robotics, we have proposed this language. And the goal here is to identify the key abstractions and sort of bake it into the language so that it makes programming, verification, and testing simpler. So this is joint work with Sasha Misailovic and Gerd Dollerud, and the leading grad students working on this at Illinois are Ritika Ghosh and Xiao She. So here is what the delivery application would look like in the Koord programming language. I don't need you to look at the code in detail, but really quickly you can identify that there are 2 events. It's an event-driven language. And these events correspond to these 2 parts of the application, like completing the application, completing the task and going to the next task, and then the assignment part. And the reason this code is so succinct is because we have this shared variable abstraction built into the language. So just like a regular program can declare local variables, Koord programs can declare shared variables, and that allows different robots to communicate with each other, but by just reading and writing from these shared variables. Now, this is the what part. So from the point of view of the programmer, you have shared variables. Now, how these shared variables are actually implemented, well, that gets into TCP/IP, ROS, and all of that stuff, which is part of the implementation, part of the runtime system for Koord, and the program doesn't have to worry about it. Similarly, we have an abstraction for sensor ports. So this defines, for example, the notion of a position, which is a 3-dimensional or high-dimensional vector, and the programmer gets to use the position of the robot without necessarily knowing how this is implemented using GPS or some indoor positioning system. You can make this abstraction even richer by adding an error bound on the position, and that could potentially be used by the algorithms. And the third interesting abstraction we have built in is this notion of an actuator. This allows the robot to specify a path that the platform should follow. And once again, the implementation could depend on PID, some machine learning based algorithms, or MPC. And as long as the programmer can direct the robot to follow a path, the rest of the program doesn't have to worry about the implementation. All right, so we have this language. What can you do with it? For starters, you can target particular platforms. For example, if you want to run this application on this vehicle, you have to compile the high-level application code with the platform-specific implementations of the positioning and the path planners and the controllers, and you get an executable. And you can deploy this executable on the vehicle and execute it, okay? If you wanted to deploy the same application on a different platform like drones, well, you take the same high-level program and you compile it with the implementations of the controllers for the drone, and you get a new executable and you can deploy it on the drones. Okay, and the runtime system makes sure that these different heterogeneous platforms can work together. And so on. So if you wanted to now add a new set of platforms to this suite, then all you have to do is develop the implementations for these abstractions for the new platform, just like writing new device drivers. But the high-level language remains stable and your application code does not have to change. We have also built a simulator for Koord, so you can compile the code with a model of the platform. So now you have to have some physics-based model of the vehicle and the drone, and you can deploy it on a large number of instances. And finally, we have a verification backend, and I'm going to talk a little bit more about it in the second part of the presentation. So I'll move on for now. Okay, so here are some videos showing the simulation of this delivery application. The simulator is actually quite high fidelity. It has separate threads for each of these abstractions that are running for communication, control, and you can also deploy the same code on heterogeneous platforms, as I said. So the second simulation here is showing a deployment on 5 drones and 3 ground vehicles. And the same code, you can deploy it on the actual hardware. So this is the Intelligent Robotics Lab we have here at Illinois, and this is running the same code on 2 ground vehicles and 2 drones. Okay, so I want to talk about another application real quickly. This is motivated by the drone shows that are becoming quite popular. And many things go into making these drone shows work, but a key part of it is creating this type of uniform distribution of the drones. And that part of the algorithm is quite simple. It's actually a distributed consensus-based algorithm, and you can find it in textbooks. It's basically at time t, agent I is going towards the center of its neighbors, or some linear combination of its neighbors. A beautiful algorithm. There are lots of analyses of these types of algorithm. And now with Koord, you can implement it in 10 lines of code. So this is the Koord implementation of that, and you can simulate it. And again, this is possible because of the shared memory abstraction, and the programmer doesn't have to worry about TCP/IP and all of these things. Although if you wanted to run it in the real world, the runtime system has to implement all of that. And another nice thing about this is because the code is so succinct and close to the mathematical representation of the algorithm, you can actually analyze it. You can prove properties of this application. Okay, so that brings me to the second part of my talk. I wanted to talk about this bigger ecosystem of development of applications for safe autonomy. And the centerpiece of this is the verification, validation, and testing. So how do you test and verify or certify code for safe autonomous systems? Now, 2 inputs go into any verification engine. There is a model or the code. For example, it could be Koord program for the application, that you want to verify. And secondly, there is the specifications or the requirements. So we heard quite a bit about specification yesterday. Hadas talked about different specification languages that came up in Sandeep's talks and in JP's talk. So I'm not going to spend too much time on specifications. Um, and the typical output from a verification engine would be one of these two things, right? So either it produces a counterexample showing that a particular behavior of the system violates the requirements. And this is useful because that can serve as a bug that needs to be checked, and then potentially the code has to be improved or the requirements have to be changed. And this loop goes on forever. This is the typical design debugging cycle. And eventually, hopefully, we get a proof showing that all possible behaviors of the system meet this requirement. And this verification loop can be applied in various different stages: early design, late integration. And you can imagine that this program comes from the development cycle or the programming language that I was showing you earlier. And ultimately, the proofs can go and serve as an artifact for the certification process. Now, just to make things concrete, let's talk about verifying applications coming from this Koord language. And it's important to note that we are trying to develop this verification engine that works for all Koord programs, right? So it has to be quite general and not just targeted for a particular robot. And the requirements here could be, for example, that robots do not collide, or the robots stay within the bounds of the extremal robots defined by this formation flight application. Now, this is a very hard problem. And in the next slide, I'll give you a sense of why this is a challenging problem, and then talk about some of the recent progress that has been made in this area. But I want to make this higher point that, verification formal methods suffers from this curse of broad stroking. So, there are very effective and powerful solutions that have been developed in the last decade or so, and sometimes they're lost in the sort of glaring hardness of the general problem. Okay, so the general problems can be quite hard, but nevertheless, there are very effective solutions once we pick a particular subclass of problems that are useful. Okay, so how do you develop a verification engine for Koord? Well, you have to start with the syntax. So the syntax for Koord defines all possible valid statements that you can write in this language. And then you have to figure out what is the state of the system. Well, we are dealing with a robotic system here. So the state includes the hardware state, the software state, and not just that, this is a distributed system. So we have to stack together the states of the individual robots to get the state of the ensemble of the entire system. And then we have to define how the state can evolve. Okay, so there are two broad ways in which the state can evolve for a system like this. Either the program executes and updates the state of the system, or some physics happens, the robots actually move. So we can distinguish between these two types of things that can change the state, and the verification system can actually decouple these two and focus on the analysis on each of these parts. So I'm not going to talk about the program analysis aspect of verification today. There's a lot of work here. We are building up on this framework that has been developed by our colleagues, Grigore Rosu at Illinois, and this has been used to check, for example, GCC, the compiler for the C language. But I'm going to focus on a particular part of the analysis that has to deal with the physics. And this is what models the movement of the car and the action of the sensors and the actuators on the models. And this, again, is a huge area. A lot of control theory, hybrid systems theory comes into the verification of this part. So let's get into that a little bit. I'm going to quickly tell you what the verification problem looks like and what some of the recent advances have been. So the traditional way of looking at this verification problem has been based on models. So if you have a model of the car, say a nonlinear differential equation, then what you want to do is this reachability type analysis. You want to compute the set of all the possible states that the system can reach within some bounded time. And it was realized in the 90s, actually, that this is a very hard problem if you want to solve the problem exactly and for unbounded time. And this is what I mean by the general problem being very hard. But then if you want to solve a bounded version of the problem and you are satisfied with over approximations, then the problem can be solved quite effectively. So in fact, there's a particular line of work that we have done, which looks at data-driven verification. So you want to use the simulation data of the model uh, together with some information about the model, like the sensitivity of the solutions to the initial state. And then with these two extra pieces, you can compute or approximate this reachable set and solve this verification problem. So now this sensitivity, let's call this quantity beta for the purpose of this talk, is a interesting thing to compute, and people had looked at linear models for which the sensitivity can be computed precisely. This was work by Alex Danze and Oded Mahler. And then for nonlinear system, the problem stayed open for a while, and then several papers came out almost at the same time. Murat Artçak has done some uh, work here that also proves to be quite effective. And the line of work that I'm mentioning here is by my former student, Chuchu Fan, now faculty at MIT. And she figured out a brilliant way of computing the sensitivity function using the symmetric part of the Jacobian and the eigenvalues of that in an online fashion. So this is what is implemented in one of our tools, C2E2. This is what it looks like. You can load a model. This is not the Koord language. This is a different way of describing a control system with potential mode switches. And you can specify the requirements, the safety properties, and then you can hit a button and it'll go and try to compute this reachable set and try to prove safety, or it'll try to find a counterexample showing the properties violated. So this particular animation here is working with a lane passing controller for vehicles. And in this case, these are the reach tubes that are computed, and it turns out to be safe. Now, so that's the case where you have a model and you can compute all these quantities like Jacobians and eigenvalues and so forth. So we wanted to look at situations where that is not possible, because a lot of controls is dealing with proprietary models, and the models are just too complicated to be expressed as differential equations. So what can you do in that case? Well, you can use learning here. And one of the ways to use learning is to choose a template for the sensitivity function that you're trying to learn, and then try to learn an instance of that template from the data. And this turns out to be actually a pretty standard learning problem. With a little bit of math, it turns out that this becomes the problem of learning a linear separator. Sort of abstractly speaking, these simulation traces are generating points, and you're trying to find this sensitivity function as a line or some sort of a shape that gives you the smallest volume containing these points between the horizontal axis. If you get the smallest volume, that gives you the tightest approximation of the reachable sets. And the kind of guarantees you would get would be the typical kind of pack guarantee. So you can find for any epsilon delta, the number of samples you need to get sensitivity with a high probability correctness. Okay, so then you can combine this, the learned sensitivity function with all of the machineries that you have from formal verification, like fixed point analysis, abstractions, reachability, to get a guarantee over the entire problem. So basically, assuming that the sensitivity function is correct, you get your over approximation of the reachable set, and you can prove the safety. So this proves to be quite effective, and it does not require all this burden of creating detailed models. And I'm going to mention a couple of case studies where we have applied this. Most of these have been done by master students who are not necessarily working in control theory. So here is the first sort of easy application of this that I wanted to mention. This is autonomous vehicle that some of us are working on here at Illinois. This is joint work with Katie Driggs-Campbell. You'll hear more from her later this afternoon. So we are building this vehicle, and there are various components to it. There's pedestrian detection, pedestrian intent estimation. That's an important piece that Katie is working on. There's decision making and control. But the piece that I want to mention right now is the reachability piece. So The reachability problem here is quite simple. Basically, what it has to do is propagate the uncertainty in the trajectories of the vehicle forward, and also it has to propagate the uncertainties in the pedestrian's motion forward. Now, this pedestrian detection and estimation is a whole other challenge in itself, but assume that that thing produces correct results. Then the reachability problem is checking whether these two predicted trajectories intersect in the future or not. And we can actually run this in an online fashion. So this is what the reach tubes look like. There's a little bit of a nesting going on here because we have different levels of confidence about the state estimation. And for each of those, we are running different reachability analysis. Okay, I'm going to move forward on this. This is the system showing everything running together, the pedestrian detection, estimation, and the reachability. Okay, so moving on, I want to finish with one other application that I think is quite interesting. This is coming from the Air Force's Incremental Autonomy Initiative. The Air Force has, of course, a lot of legacy systems, different kinds of control systems, and they are building new autonomy features on top of that, sort of like driving assist systems. And what you want to check is that the new autonomy features play well with the existing features and control system. And this is a hard problem. You're dealing with compositions of various different kinds of control logics and state machines. So the particular thing that we are working on is this auto GCAS system, the ground collision avoidance system. This is supposed to ensure that the aircraft does not run into the terrain if, for example, the pilot is unconscious. And this can happen because when the pilots do very high G maneuvers, then the blood can, the blood supply in the brain can fall below a threshold and they can basically pass out. So this is a declassified video that shows the GCAS system in action. You will see that it's pretty loud actually. The pilot is sort of uncomfortable, and then at some point the aircraft sort of goes into a nosedive, and then the GCAS system sort of kicks in and pulls it back up again. Yeah, so that's when the GCAS system pulls back up and brings it back into a nominal trajectory. All right, so again, individual simulations are pretty tricky here because there's a lot of uncertainty about the state. The state estimation is running on various different sensors, airspeed, altitude, attitude. And so you want to propagate this uncertain reach tube forward for this analysis. So I'm going to show you some preliminary results that we have obtained from this system, applying this technique that I mentioned earlier. And so we are combining this learning-based sensitivity analysis together with formal logic to verify this system. And so these are the reach tubes that are computed by this algorithm. The pink envelopes here are the reach tubes. And the system is pretty complicated, 20 plus dimensional, and it's quite nonlinear. And of course, we don't have access to the actual system. We're working with the black box model. All right, so takeaways from this talk. It's possible to create abstractions that separate the physics from the logic, at least in the context of these distributed robotic applications. The results seem promising. We can port code across different platforms, and we have developed several different applications, excited about the new applications we are building for agricultural robotics with Girish Chowdhury. And the second message I wanted to convey is that there's a tremendous amount of progress that has been made in verification and validation from various different labs across the country. And one of the main things that is driving this is this deeper connections between control theory and computer science and formal verification. Data-driven approaches are becoming quite powerful. And also there's new data structures that are getting invented all the time, driving this innovation. So if you want to learn more about that, you can take a look at my book, which is coming out next year. And finally, I think there's a huge challenge in this area in creating open benchmarks. And for verification, I think it's a little bit simpler because you can create a model and write down the requirements, and that constitutes a benchmark. But for control, it's more challenging because the interface for a control problem is harder. You have to specify what the inputs and the outputs are, what the environment looks like. But I think there's an opportunity here to create interesting controls and autonomy benchmarks that the community can get together around. Okay, so I'm ready to conclude. Thank you again for your attention. And this is the research team. All of this is done by a fantastic team here at Illinois. So thank you.
Thank you so much, Sayan, for that great talk. We're starting to get some questions already. And I'll ask, I think we have room for maybe 1 or 2 questions. So I'll ask a question that's already come up, excuse me, on the chat. And this is from Victoria Tuck. She asked, could the Koord system allow for the implementations on different platforms to share information? For example, before you had homogeneous drones avoiding each other and homogeneous cars avoiding each other, but could you have multiple heterogeneous car platforms able to use this and share information and operate in the same space?
Yes, absolutely. Of course, for every new car platform that you want to introduce, you have to do some work in creating the platform-specific implementations of the controller and the message passing system. But once you have that, then we have this abstraction, which is the different cars can talk to each other through shared variables. So let's say you publish your path as a shared object in this table, then the different types of cars that are looking at the paths that are being followed could avoid those paths. And that's exactly what's going on in that deployment that I showed you with cars and drones. So these are different heterogeneous types of vehicles, and they're avoiding each other because the paths that are being followed is actually shared using the shared variables.
Thank you, Sayan. And I'll ask others if they have questions, please ask them on the chat, or you can unmute yourself and ask a question.
Yes, I would like to ask a question.
Yes,
Sayan,
sure.
great talk. Can you tell us a little bit about how do you model environments in Koord? I mean, in the EDA industry, it was a very closed environment. The circuits are very closed environment. Robotics, you're in an open environment. So how is this affecting the language constructs? That would be my question.
Yes.
Thank you.
Yeah, so that's a great question. And we don't have a perfect answer to that yet. What we do allow is, I'm going back to my slide showing the semantics of Koord here. So there is a rule here which says how the environment evolves. So CP prime here is basically showing from the point of view of a robot's program how the sensors changed after one round of evolution of the environment. And that function F there tells you how the environment evolved from the point of view of the robot's sensors. And the thing that we do allow is that this function could be a black box function. So this could be, for example, a very complicated simulator which has a model of a LiDAR, LiDAR bouncing off the obstacles and what have you. And that would still be an executable semantics of Koord. Now, what kind of analysis you can do with this black box function is a whole other question. So probably not a whole lot right now, you can just run it. On the other hand, if you had a very simple model of your environment, let's say nice geometry and nice kind of proximity sensors, then you could actually do some analysis based on that model of the environment.
And then maybe I'll add another question onto that. Maybe it's a little bit of the tension between verification and synthesis. So in this framework that you presented in the second part of your talk, Can you maybe speak to the possibility in the kinds of approximate reachability, for example, that you're doing? Is it possible to still think about like the control synthesis problem of being able to, synthesize safe controllers using the abstraction that you're computing?
Indeed. So there's several different aspects to it. So one way that synthesis can come in here is, okay, you have figured out the sensitivities of the individual modes, and you can synthesize a high-level controller which switches between these modes, right? And how you stitch together these modes might be relative to some requirements that you have for maintaining safety or stability. So that's one way of doing a synthesis, and there is some work that I can point you to that tries to do that. The other way the synthesis comes in, and this is actually work that is appeared recently by Chu Fan and others in the Coral conference, is while you are learning this sensitivity function, you also have control, right? So you could learn the control so as to get the best sensitivity. So in that case, you are sort of jointly doing this control synthesis and minimizing the sensitivity of the system to that control. So yeah, these are all pretty exciting directions, and many different ways of combining learning with formal methods. Another one that I haven't mentioned is, instead of learning sensitivity, you could be learning something else about the model, right? Like a Lyapunov function or something, and using that for synthesizing some high-level switching logic as well.
Thank you, Simon. I think we've gone a little bit over now with our questions. We have to end the session. So thank you for your talk. Thank you to both Cyan and Peter for a great start to the day. We have a little break now. Our breaks are always getting shortened, but that's a good thing. It means we have a lot of discussion going on. So we'll take, I think we'll just take a 6-minute break. We'll come back 15 minutes after the hour, and we'll resume with our second session. And the first talk in that is Anka's talk. Good. See you in 6 minutes, everyone.
Thank you very much.